All right. Welcome back. Why does it say waiting? There we go. All right. Day what? 22? 22 today? Um, dang. 3 more days? Is that it? Is it 2 more days? Something like that? We're almost done. Day 22 or 21 to day 22. I didn't mess up anything too bad. Yeah, okay, my mic's still working. Yeah. It's a day for a parser. Okay. I mean, I'm happy with that. I'm okay with that. Get rid of this. Day 22. Code dot. Let that open, and then let's check it out. Let's see what we have today. Calendar 22. Something about cuboids. Reactor core is made up of a large three-dimensional grid made up entirely of cubes, 1 cube per integer, three-dimensional coordinate. Each cube can be either on or off. At the start of the reboot process, they're all off. Could it be an old model of a reactor you've seen before? Is this... Oh no. Oof. To reboot the reactor, you just need to set all the cubes to either on or off by following a list of reboot steps. Each step specifies a cuboid, the set of all cubes that have the coordinates which fall within the ranges for x, y, and z, and whether to turn all the cubes in that cuboid on or off. For example, given these reboot steps, so I guess this is going to be our first test input. The first step turns on a 3x3 cuboid consisting of 27 cubes. Okay, so we've got like basically cube pixels here. That's what I'm gathering. Second step turns on a cube 3x3 at 11 and 13, whatever. As a result, only 19 additional cubes turn on. The rest are already on. Third step turns off. Okay, so right now I'm thinking like if we're just going to be arbitrarily turning stuff on and off, we're going to use a hash map. Because it doesn't sound like this is like a defined amount of space. It's just like arbitrary, like there. So maybe we just BTreeMap it. Oh no, oof does not sound good. Okay, 39 cubes are on. The initialization procedure only uses cubes that have x, y, and z positions of at least -50 and at most 50. For now, ignore cubes outside this region. For now? Okay. I'm still not going to use like a 3D array because F that. Oh, there we go. There it is. -54,112. OBS scene switch, please. There we go. That's what happens when you mess with settings. I was messing with camera settings and stuff yesterday. So, yeah, you got face cam for a bit. Congrats. Last 2 steps are fully outside the initialization procedure area. All other steps are fully within it. After executing these steps in the initialization procedure region, 590,000 cubes are on? Come on, really? execute the reboot steps afterward, considering only cubes in the region 50 to 50. How many cubes are on? Okay, well. I think this is BTreeMap time for us, because basically the input here will give us a set of X, Y, and Z that we can just loop over, and then we can insert, and BTreeMap will let us check all of those positions, and if we have any of those positions that exist, then we can operate on them. If we don't, then we skip it. So I think for part one, at least, makes a lot of sense to do just a BTreeMap and start inserting a bunch of stuff. Let's get a test going. Get rid of that. Get rid of all of this. I bet you doing... I still want to do the cargo generate thing, so maybe I'll do the cargo generate thing, like, hilariously, somewhat after I do all of these problems this year. Get rid of that. Write a test. This isn't going to be like the test input, so maybe we just do const input. Let's call this const input 2 or input 1, which is going to be the same thing. It'll be a static string or whatever. If I can type, dang. Static string slice equals this. You thought it was an intentional face cam as you got started. I know, right? So, like, I mean, it could have been, right? Who knows? If Nikki never asked, maybe you'd get more face cam the entire time. That def works and is exactly what I did. The BTreeMap, yeah. I mean, it seems like the most reasonable approach to part one. I don't know what part two is, but let's build a point struct will be helpful in part two. That's exactly what I'm going to do. Although it doesn't actually matter for part one. Automation before repeated work. Lots of test input today, which is nice. Okay, so we are in part one. Let's do input one. It's the wrong thing. Input one, right? And then we need what, like a command list, basically, out of this. These are all positives, but there are negatives, right? So we're going to probably parse an I-32 out of this. There are negatives. The negatives are fairly large. Is our puzzle input just like absurdly massive for whatever reason? It doesn't look like it. It does mean that we're going to have like an absolute boatload of items in our BTreeMap. But we never really hit any indexes that are bigger than like 100K in either direction. So I think we can just go with like an I-32 or something. Do we have a thing to test here? We'll have a command step. So what are there? 3 steps. I'll leave the command steps for later, but the test that we're going to do here is going to be like test part 1 test small input, And then we are going to probably like parse step. I think there were 4 of them or something like that. So we're going to step, and then check sizes. We're going to check the sizes at each step just to make sure we're doing the right thing. So you know what part 2 is going to be? Unused input lines. No, we don't do that here. I think my part 1 was like 15 megabytes in total. Still not the worst one that I've done like this. The part 1 only considers points from -50 to 50. True. Okay, so let's get the parser running because that seems to be the easiest thing to start with. Let's do struct point x I32 y I32 z I32, and we're not doing ND array, so I can call them what I think they are. I'm going to put debug on this just to start off, and then also eq and partial eq so we can test with them. And this is going to be, I'm going to do the same thing right here. Derive, debug, struct command, not struct, enum command. It's going to be on x, y, right. It's going to be on from point to point, maybe? Or off from point to point? That's how this works, right? From 10 to 12, 10 to 12, 10 to 12. It looks like these are all regular. Are they all the same? So this is 46. This is a little bit more than that. That's 54. I sure wish debug was derived by default in my advent of code directory. I derived that for 100% of my structs. Yes. You know, I go back and forth. I feel like I like the fact that it's not by default, but it also is something that I basically derive on everything. So we can always change it. So I'm just going to go back up and keep going. I bet you we're going to do a triple Cartesian product on this to get all the points. Let me pull this up a little bit. This is going to be a Debug Commands, right? Because really all we parse is the commands separated by new lines. This is going to be command. So fn command. So we do a subparser for command, right? We take the input, which is a string slice. We return an I result, string slice, and command. And this is going to be let input I think we need this. Action equals alt tag need alt to be imported here, so we'll do non-branch alt. And this is basically just saying it works for on or off, but nothing else. The input throwaway equals tag space x equals input let input low x high x equals separated pair. Is separated pair take the tag? I think it just takes the string. It takes the tag. It takes the parser. So we do dot dot and then complete I32s on input. And yes, this is how I write code in real life. I just write to the end of the line and then be like, hey, Rust Analyzer, can you help me out here? It's not separated pair one, right? What am I doing here? Nom latest docs separated pair. It is separated pair. First separator, second. Ah, right. It's three. That's why it's complaining. Oops, that's the wrong button. Okay. So we got either on or off, the X's, then the Y's and the Z's. Did I really just do that in the middle of the... That's rough. The X's and then the Y's and the Z's. So we do... Wow, I'm just not putting my cursor in the right place today. The Y's and the Z's. We still need the comma. So we're going to do this same like throwaway thing. And we're just going to do comma. And comma. And then we should have everything at this point, right? So we will have here match action. And it's either going to be on or it's going to be off. Or it's going to be a big problem. So here we do command on, and then we do point X, Y, Z. This is going to be low X, low Y, low Z. And then we're going to have the same thing, and these are going to be all the high variants. High. Right, I named them that, low and high. Cool. So command on, point. This needs to be command equals this. And then we return OK with the input and the command. And then we need to copy this and do command off. Why is that not working? That's weird, right? Get rid of these two, and then get rid of these two up here, because this is a tuple, and we didn't make it a tuple. Okay, so we've got a parser for all of our command lines. We've written parsers before in Advent of Code, very many of them. Hopefully that was fairly familiar. What we have here is a struct with an XYZ for like the low end points. So like the lowest X, the lowest Y, the lowest Z. We have a command structure here that will take either tell us to turn something on or turn something off. And that comes with a low point and a high point, basically. We have the command parser, which parses each individual command line. First, we take the alt parser, and depending on whether it's on or off, we parse one of those. If it's not on or off, then we have a problem. We throw away the x equals, and then we actually parse the low and high x values. We throw away the comma. We parse the low and high y values. Same thing, same thing. And then down here, we match on action, which is a string slice. So it'll be either on or off. But we can't guarantee that because it's a string slice at this point, and doing anything more sophisticated with the typings here would require a dependent typing system to be like, hey, this can either be on or off, which we don't have access to, and is actually not super ergonomic to use in most cases. If you're interested in that kind of thing, languages like Idris do a lot of it, but typically we don't do a lot of that outside of dependently typed systems. If it's on, we use command on. So we initialize the on variant of the command with 2 points and off with 2 points. And I'm not sure that keeping 2 points is the right move here, but you know, seems like a good idea at the time. So when we do this, we get a list of commands and we return that. And this is commands, and this is not going to be mutable. So yeah. See, what are y'all doing? The dimensions are not the same size, unfortunately. Yeah, I saw that. The Cartesian product or triple nested for loop. We're going to do Cartesian product because I don't want to do triple nested for loops. I actually had to do Cartesian product because my triple nested loop had iter ownership issues. Ranges only into iter. If you have ownership issues with ranges, you can always take ownership of them. Right? Copying, I would say that copying numbers around is not that big of an issue. Like you can always go back and optimize it. So I would do clones and I would copy and I would do all of that stuff before I changed the problem, probably. Okay, so we've got commands, and commands is going to have to run through a function, right? So we're going to have to like have a function called tick here. Tick is going to take a grid, which is going to be a BTreeMap, like we talked about earlier, a BTreeMap of point to on off. What do we call on off? Bulb, which we haven't made yet, so don't we still need to make that. So enum bulb here, right? And then it's either on or off. We'll derive debug and eq and partial eq. So we take the grid and we take the command, which is a command. We don't really need ownership over this, so I'll take a reference to both of these things. And then inside of tick, I guess we're going to modify the grid. That seems to make the most sense. So we're not even going to return anything from this, I don't think. I think we're just going to modify the grid. So here, let's do a let grid. Let's do let mute grid. Right? No, let's do let grid equals BTreeMap new. And we will, how many times do we need to tick this? One for each command. So it'll be like commands iter and then fold, I guess, would be a good one. You can pass this BTreeMap in. And then we take an accumulator. Let's do starting grid here. This is grid and command. And this is tick grid command. So you can see where my brain was at with the let's do a cargo test here because I'm getting some failures. BTreeMap found unit. We're just going to pass grid back, mute grid because we don't have the mutability on this. So that should be it. Input. Oh, part 2? Why is it running part 2? Hang on. 112. Our input is not doing this correctly. So new line, I wrote the parser wrong in some way. Let's debug commands here. It sounds like we're going to get an error. Yeah, I definitely think the Cartesian product thing is the better approach there, Derek. I also just do not want people to shy away from cloning and copying. I don't think that that's like, if you think about it in your head, and I know that this wasn't necessarily relevant to your situation, but if you think about it in your head, cloning and copying things around all over the place is basically the same thing that you're doing in JavaScript everywhere, right? Like, just because we can identify and think about the places at which we are explicitly doing cloning and copying in Rust doesn't mean that we actually have to do anything about it, right? Because we're already writing code that is more performant, that is more resource use, that is more resource efficient than like the JavaScript that we already would have written, even with a bunch of clones. So something wrong with Y, because I didn't put this in. Let's look at the test input for a second. X equals ... comma Y equals is what that is. Comma Y equals, comma Z equals, and that should be good. Cool. So that looks right for the parser. So we tick, and when we tick, we have a command. I think we're going to build up the Cartesian product from each of these ranges. So we're going to do match command. We can just drop these in. This will be point XYZ, point XYZ. Right, I'm just going to call them Z1, Z2. This whole thing is a tuple. And then we're going to do the same thing right here. I'm getting some type errors because I am now destructuring the wrong things. That's, we can just do like 0.1. I'm going to call them low and high instead of destructuring here. And then both of these do the same thing, right? So I think what I'm going to do is actually return this tuple, point low, point high, let points equals match command. And then right here we do let all points equals we're going to do low and high. Low dot x dot low or high dot x dot Cartesian product low dot y comma high dot y dot Cartesian product low dot z dot high dot z. And then we're going to need a dot map here because what we're going to end up with is a nested tuple. So we end up with tuple x, y, z. And what we want out of this is point x, y, z. And this needs to be dot dot right here and not comma. So we end up with all points, which is a map of all of the points, basically an iterator that is all of the points in all of the cubes. I think we then take this and do, what do we do here? We have to insert into the grid, right? Point in this giant monstrosity. Grid.entry point or insert op let's do let op equals match. I guess we could already do this, right? Op here. And this is bulb on. And this is bulb off. Or insert off. And modify value equals op. It's going to be a reference, or maybe I got something wrong here. derive ord right on what point? There's also like a multi-Cartesian product in iter tools. Yeah, I've just never used it before. We could try it. I think what I want to do is I want to come back and try that, Derek. I'm going to use the Cartesian product here because I know it works. And from what I'm gathering, part 2 is a whole thing. So I want to get through this first, and then we can come back. Remember that I said that we should come back, and we'll do multi-Cartesian product and see if we can see what that does. The trait or does not implement every point. Now it is. We do not have to try it. I was just calling it out because it's a thing. No, I want to try it later. So that was me like setting the boundary, right? Like I want to try it, but I know that this Cartesian product approach is going to work. And I also know that part 2 is going to be a bear of a problem. So I want to do it this way without diving into something else. And then we can come back later and compare Cartesian product and multi-Cartesian product if we solve part 2. Oh, it's a BTreeMap, not a set. My bad. It is a BTreeMap and not a set. Curious if this is how the product macro and iter tools works under the hood. I don't know because I've never seen the product macro. You mean iProduct? Now you've got me looking already. So creates an iterator over the Cartesian product of iterators. Iterator element type is A, B, E if formed from iterators I, J, M with element types A, B. Okay, so this iProduct would have worked for us as well. The multi-Cartesian product also... The multi-Cartesian product I don't think does the same thing. Not unless all of the inputs are the same. Because we've got 0 to 3. We map over it and we return... Oh, I guess we do get 3 here. This example is so confusing. They should have just used 3 separate ranges. So multi-Cartesian product is if we have like an array of ranges, then we can combine them into like a vec of tuples effectively. We don't have an array. We could create one. The iProduct thing is really interesting. I think that cleans up the code quite a bit. So I think I can just drop that in. The example is so bad, which is why I went with the iProduct macro. Yeah, for sure. You have to only check for negative 50 to 50 cube. You must omit all others if RAM will run out. I don't think RAM will run out. I don't think that, I mean, like, I've got 64 gigs of RAM on this machine. So, like, I'm not super worried about that unless it's like, unless they intentionally made the amount of space to be more than any computer can handle. But yes, you are correct. We do need to ignore things that are those sizes. Is it any point or is it any intro point? The initialization procedure uses cubes that have X, Y, and Z positions of at least negative 50 and at most 50. So all of them need to be greater than or equal to or less than or equal to. Is it? I see a negative 50 in here, so we use that one. And I think this is inclusive, so negative 50 to 50. So for tick, for the moment, we could also iterate over the commands, right? So maybe we do that instead. I'm going to filter out the commands. Yeah, but that means if any of the low X or low or high X are out of the range, right? So let's do dot B dot Y point A dot Z. Actually, that's so we can do what is it? Let valid range equals what is it? Negative 50 dot dot equals 50. So if dot clamp, what is dot clamp and what type is it on? A value bounded by a maximum and a minimum. If the input is less than the min, this returns min. We don't want clamp though. Oh, I wonder if it's because they overlap enough that it works either way for the negative 50-50. I think that the problem is set up in a way where what they mean is not actually like the thing, right? All of this input right here is somewhere between negative 50 and 50, and these are very clearly not, right? And I don't think that if this crosses over negative 50-50 that we're supposed to like operate on it. I think what they're saying is, hey, ignore a couple lines here, not making the problem ridiculously more difficult for no reason. Right, because this is supposed to be a cube, right? It's supposed to be the definition of a cube. So only the cubes that completely fit inside of that region. Okay, so command A, B, this is going to be I'm just going to vec a dot x, a dot y, a dot z, b dot x, b dot y, b dot z, dot all, val. This is actually the valid range. Valid range dot contains val. It should work, right? Command isn't a thing, so we need to AB, AB, Just making this super simple, basically, for the moment. So we do all this, expected unit found a reference to bulb that we're going to have to get back to in a second. No method all found for struct vec dot iter. So here we are filtering for any points that have a starting or ending position outside of the range. And then we go back up here and we need this used after move. We're cloning this, right? We get op here. This is .clone. We're just going to create a new one for each of them because they're not all going to be the same. We have an implemented clone up here, so we're not allowed to do that right now. But it doesn't matter. We can just implement clone, and then everything's great. Gravy train. And then we fold it, let final grid equals this. Debug final grid, and we should have something with points in it. So final grid is this thing. I now present this thing. Okay, so the first step turns on yada, yada, yada. So we should have 39 cubes on at the end of that one, right? So let's test that before we even do this other monstrosity of a test, I guess. Actually, let's just run the whole thing for this one, and then we can do the other one. And the test fails because we still aren't returning the right thing yet. And let's get rid of the debug for commands. And final grid. This is going to be final grid length, is it? Final grid dot iter dot filter kv where v is on, right? Dot count. And then there's probably a references issue here. Yeah. Oh, we don't implement copy here. That's fine. We can do that. I'm not worried about copying an enum. Okay, so we get 14, which is the wrong answer. This doesn't give us like the list of stuff yet, does it? It does give us this list. I don't particularly want to reparse all of that. Let's do this instead. Let's do fold, tick, grid, debug grid here. Let's do actually, instead of debug grid, let's get an output that is going to be similar to the input in the advent of code problem. So let's do grid.iter. For point in grid.iter. This is going to be point and status. So let's just call this bold. Print line. Yada yada. I think there's a way to print that out nicely, but I can't remember it off the top of my head, so I'm not going to do it. So what I'm going to do is this monstrosity. Point.x, point.y, point.z. And that should just print out all of the points that we've touched, basically. So let's do print line step. And let's do we're just going to debug that for ease of use. And now we see all of our stuff. So here we start with number 1. Pull this over to the other thing here. Okay, we start. The first step turns on a 3x3 cuboid consisting of 27 cubes. So this is wrong, right? Three by 3x3. Is our Cartesian product wrong? We get 10, 10, 10, 10, 10, 11. 10, 10, 12 is not in the picture. I'm not doing inclusive ranges on those, am I? Where are we even doing those ranges? Dot, dot. Yep, there it is. Not doing inclusive ranges. Come on. Dot dot equals. Dot dot equals is probably going to be fine. Yeah, and now our test pass. So just a lesson to make sure that you use the right ranges. I did exactly the same thing last night. What's the difference between end v equals on and v equals on? One is is considered destructuring the shared reference, which is something you can do. So I guess let's talk a little bit about this. Where did I do that? Okay, so right here we have filter, right? And filter is doing what's called a destructure on the shared reference here. So you can destructure structs, enums, you can destructure shared references, you can destructure a bunch of stuff, right? Here we're destructuring a shared reference, which means that v gets copied so that we can do this comparison, right? And I'm not going to get into what copied means specifically, but because we did this, we had to implement copy on bulb. So if we go back down, if I can find it, if we go back down now, we see that this line with the previous shared reference, the line with the previous shared reference, let's see if I can make, The line with the previous shared reference now has no implementation for like a double reference to a bulb compared to a bulb. But we can also solve this by dereferencing V, right? The only problem is I believe that we need to dereference it twice. Yeah. So if we dereference it twice, we basically get down to the value that we can compare. If we bring up the Rust analyzer types, you'll see that V is now a double reference to a bulb. It's a double reference because we are iterating over the grid and then filtering, which also takes a reference. So if we do this, you can see that we just get bulb because the Rust compiler is just like, yeah, obviously I'll destructure the shared references and return you a bulb. But to do that, it has to copy that data in. So if we put copy back up there and we come back down here, we see that everything, the types all work out and we still are fine. So this closure acts as a function, right? And thus when we destructure a shared reference off of something, what we're basically saying is copy this in for me. And a reminder that the copy trait is just a copy of bits. If you are a stack and a heap oriented kind of person in your head, I believe that this closure creates a frame, and that frame takes some arguments, right? So it takes the destructured argument here. And as a result, those bits for the value get copied into the stack for the frame. So this function gets a copy of the argument instead of getting a reference to the argument. And that's the difference, basically. You can either dereference back down to the value, or you can destructure the shared reference. So the Rust compiler does some sugar. If you do the NV thing, it turns NN bulb into bulb. The Rust compiler, the way I'll put it is the Rust compiler does a lot for us when you're not paying attention. The Rust compiler includes something called auto dereferencing and stuff like that. There's a lot that happens that you probably, unless you're really paying attention, makes it easier to use the language because you don't have to think about every little thing. But the Rust compiler, it's just the Rust compiler being smart. So, yeah. I don't know what this compiles into specifically, especially on the ASM level. We could go figure that out. We are not going to do that on stream today. But there is a site called Godbolt. So let's just throw this in and see if it works. I don't actually know if this will work. I don't use Godbolt that often. Let's do hub fn main here. And then use standard collections BTreeMap. Oop, I didn't want to save that. Oh well. Where's Bulb? Bulb, where are you? There you are. Failing for mismatched types, that's fine. The BTreeMap isn't specified, so we need to do BTreeMap. And we'll do like use size to bulb, because that's kind of what we have. And then you can see actually everything get compiled here. So if you're really, really interested, you can take a look at the assembly level stuff. There's a lot of it here for just like, because we're using a BTreeMap. If I was going to show this off as like an educational example, I would find something that didn't use a BTreeMap. But yeah, so you can go here, you can do this. It's very interesting. I don't really do a lot of assembly level debugging, so I don't use it that much, especially for like the kind of Rust that I write doesn't really require me to do a lot of assembly level debugging stuff. I really write like CLIs, serverless functions, things like that. But you can get this information and you can get it out of like a regular Rust program if you want to. There's also view her, not inside a function body. Let's go grid entry. Is it grid entry? No, which one were we looking at? Where's the shared reference? There we go. So if we view her, I'm going to have to make this fully big. But Rust Analyzer also has like debugging tools that will show you the intermediary representations of Rust itself. And this is higher level, right? This is like an AST kind of thing. So we're in process part 1 here, and you can see like path, mod path, whatever. Method call with a receiver. The method name is expect because we're expecting on the puzzle input. If we go all the way down here, maybe we can find. It's a lot of output, so it's tough to like show in a useful way. Has semi, expr, segments, V. So V right here. There's a path, binary operation, a lambda. The lambda is the thing that we are doing. Return type. The body is the expression 111. I think 111 is this one. So the body is the binary op. Left-hand side, right-hand side. Do we get... You can see like, when I say that like bulb : on is a module path, you can actually see that represented in the Rust AST here. And this is the HIR intermediate representation. I forget what the H stands for, but there's HIR, there's MIR, there's like Rust compiler has a couple of different intermediary representations. Whereas like if you're working with JavaScript, we just think about it as going like into Babel and back out. Which kind of just has like the one AST or whatever. Rust has multiple, so you can work on any level that you want to. But yeah, you can see text to V, generic arguments, none. I don't see anything about the reference though. Final grid, fold, iter, lambda. Lambda args pat 28. Maybe this is 28. Path, mod path, segments, text B. That doesn't feel right. Archetypes, body. But yeah. So there's a lot of stuff you can do to check out and learn a little bit more about these things. I don't think that this actually includes, or at least I can't find it right now. The HAR looks very similar to the stuff you'd find if you were building procedural macros and using the syncrate. Yeah, I think it's exactly the same thing actually. Or not, maybe not exactly the same thing, but it is very similar. Right, like when you're operating on syn and you're operating on exprs, expressions, that's kind of what these are, right? And that's because you get a token stream in from like the syn macros and stuff like that. So yeah, anyway, little detour there into how to debug stuff and where stuff goes. Is this in the shop? No, it's not. Cool. So final grid stuff, back to the problem. I could get distracted by looking at this stuff all day, actually. So, maybe we'll get a couple more videos on, looking at the HIR and stuff like that in the future. Okay. Our test worked, right? I was just kind of like explaining stuff. Yeah, cool. Let's get the input. I'm standing here talking about absolutely random shit when we could have solved the problem. Getting phantom leg vibrations. Unintentional nerd snipe? Come on, that was pretty intentional. Get the input in here. Save. I'm just going to run this because I feel like it. Probably would have written more tests otherwise. Oh man, I left the bugs in there. All right, where's the print line? That's going to be super annoying. Let's get rid of that. Cargo run part 1. Unintentional nerd snap, but an interesting one. Yeah. I find all that stuff very interesting, actually. I got the Rust compiler compiling on my M1 Mac. It's pretty good. I love it. Gold star! So I have Rust C compiling, and I really enjoy using it. So I'm going to actually contribute to the Rust compiler soon. Probably early to mid next year. I have a couple projects that I actually want to go into and start contributing back to. Like Bevy is a project I use a bunch. Like Cargo and Rust Analyzer would be fun to contribute to and stuff like that. You know, I've got a list. Okay. Now it's complete. You can reboot the reactor, starting with all the cubes off, run all the reboot steps for all the cubes in the reactor. Considering the following reboot steps. After running the above reboot steps, this many cubes are on just for fun. 474,140 of those are also in the initialization procedure region. Starting again with all cubes off, execute all reboot steps afterwards, considering all cubes, how many cubes are on. So y'all are telling me that I can't just reuse this, right? That's what y'all were kind of vibing with. I'm going to try anyway. But just you wait. I'm going to try to brute force this. When my computer crashes, y'all can be like, we told you. Until then, we're just not going to filter anything here anymore. Try to reuse this for shits and giggles and watch your RAM usage. I think I have RAM usage. CPU. Memory. I think I can watch this. Memory. There's memory. Should we try to free some up? Is that what we're going to need here? Is memory usage the only requirement here? Because we could do references to stuff instead. Let's do it. Cargo run bin part Let's do release bin part 2. Because that only has one dash. So memory, right? That's what you want to watch? $25 gigs. $26 gigs. $27 gigs. How many gigs is this going to be? Like at some point, should I stop it? Almost at 30. There's 30. Jason's elevator music. Just imagine it in your head. What is many gigs for 300, Alex? Yeah, you should stop it. It's a ridiculous number. Like, how ridiculous? Like terabytes? What's the memory usage on this going to be? Like, I was imagining Chris singing for my elevator music. I have 64 available, so we can go for another like 10 gigs at least. Oh, he said the calculation previously? All right, I will leave that up and I'll go check. Scroll back. Not seeing it. For part 2, I calculated a need of 10,000 gigs of RAM. That's a lot. All right, well, I don't have 10,000 gigs. I have a lot of RAM, but I don't have 10,000 gigs. So obviously there's an alternative way to solve this. I don't know that I know that alternative way. Quick, get more RAM from Google Drive. Yeah, let me just download some RAM, y'all. All right, we're at 54. We're now evicting cache, it looks like. All right, time to kill this. Oh, look at that. My memory is down to half. Okay, so it's a memory usage issue. I'm assuming that no matter what we do here, we run into that memory issue. The things that we're storing are not that big. Are you using 28 gigs of RAM right now? Yes. I'm using 28 gigs of RAM right now. I think that is, I think that Mac in particular tends to eat RAM. Are you sure VS Code is not bloated? I mean, VS Code is not using 27 gigs of RAM. I'll put it that way. Mac OS, like this number doesn't necessarily mean I'm holding that much in memory on a Mac. I do also have Chrome open. That is true. Oh, it's the reserved is showing. Okay, yeah, I think so. I think that's true anyway. I don't look too deep into the iStat stuff, but I believe that that's what it's talking about there. Doesn't all Nix Debian not recycle memory unless it actually uses it? I think something like that. Okay, so clearly there is a way in which we need to do cube calculations and then like the intersections of cubes, I suppose, and just start calculating numbers, maybe. Right? Because we can define a cube based on the low point and the high point. So if we can do that, how would we find the overlaps though without like iterating over everything? So my thought is basically like we can define cubes by low point and high point. Then we can define that entire area as on or off, which is a much smaller representation rather than storing everything. We can basically do something like calculate the intersection between two cubes, which is going to be painful, but it's doable, right? Like if we have a cube that is like at 0, 0, like 2 by 2 by 2, and then we have a cube that is like at 1 and is also 2 by 2 by 2, then we clearly overlap there, right? Because we have 0 to 2 and 1 to 3. So we end up with like 4 cubes overlapping, which we can detect and determine. I wonder if that's a valid approach. Because if we can go through here basically and what does the input look like? So we have these boxes, right? Like 10 to 12, 11 to 13. This feels like it's going to be a lot of little steps. And I don't know that it's going to be the most interesting programming exercise to show on stream. It's going to be, in my head, it's going to be like, check the bounds of the new rectangle against the old one, create a new box that either represents like the chunk that you're taking out of the old box or whatnot. The other thing is we can subdivide the cubes. So if we have like a giant cube, like imagine a giant cube, right? Where there's like 4 sections on top and 4 sections on the bottom. So it's like an 8 cube. And one of those cubes is like, we have to turn it off. So we turn that whole thing on and we turn one of those squares off. So 1/8 of the cube turns off. We can do, I think, one of two things, right? We can either do, we can keep that other cube around, the one that turns off, and just stick it into the list. And then I think when we go through, we can do a count of all the on ones. And then for step 2, we turn that cube off, right? The number in that cube off. And then we keep doing that kind of thing over and over. So we basically only add to everything by creating more cubes. I think those numbers would work out. It's a little bit finicky to do in my head. The other thing is we can subdivide, right? So with that like cube inside of the 8 cubes, so 4 on top, 4 on bottom, making one giant cube. If we take out one of those corners, what we end up with is any number of things really, but what we could end up with is 7 other cubes, right? Or 3 other cubes, one that just covers the top, one that covers the sides or whatever, or the bottom sides. So then we end up with basically like 4 cube definitions where 3 of them are on and 1 of them is off. And then we just throw the off one away. And in that way, we could like subdivide these cubes down into basically just being point and point. And then it's just a count of the number of spaces in that cube, which is like what dx times dy times dz. So that would all work. I think that that's not going to be the most interesting thing to program on stream, though. That is probably going to be a lot of me being like, okay, what do I think about this cube? How should I subdivide it? That kind of thing. And it's going to be very finicky. So I think I'm gonna call it at part 1, and then I'll work on part 2 off stream, and I can explain it tomorrow, rather than sitting here for 2 hours as I write individual instructions for cube merging. That doesn't sound like something that would be entertaining. But we do have those 2 approaches. We have the create more cubes approach, and we have the subdivide cubes approach. I think in the end, they become basically the same thing. What we end up with is we can define cubes based on the high and the low point. So as long as we keep the high and the low point around for any given cube, we can subdivide it into more cubes. And we can do that with like y minus y kind of math, right? It's not anything complicated. It's just finicky, and I have to write a lot of it. So that's going to be it for today. Thanks for hanging out, everyone. I will do the part 2 offline, and I will get back to you tomorrow morning with the next stream. And we can talk through it then. Thanks for hanging out. And I hope you have a great week.